Okay, so let's talk about deformation of solid. So let's say I have a spring here. So let's say I have a spring. So this spring has a original length which is L naught. So if I apply a small force, so this is a small force, and this spring eventually we know that the spring will extend. So this is the extension here, X. Okay, so if I release my force, so this will eventually returns to its original shape. So this spring returns to its original shape. We call that this spring is actually obeys Hooke's law. By saying that F is actually directly proportional to the extension. Okay, so this so in this condition we can say that um, it does not exceed the elastic limits. So this is how Hooke's law works. Okay, since the spring does not exceed the elastic limits, so what if, okay, so let me erase this one. So erase this one as well. So this one as well. Okay, so what if I apply a large force to this spring? So we know that this spring will be extended until very long. So this is our L. So this spring will eventually be extended until very long. So if I release this force, so what if I release my force? So we can see that this spring is actually slightly longer than its original length. So this should be L prime. Okay, so in this situation we can say that it's the spring is actually exceed the elastic limits. So this is what we call plastic deformation. Begins. Since the spring, the force applied has already exceed the elastic limits. So this is force exceed the elastic limits. Okay, so this is how the deformation of the spring works. So let's say we have another example. So let's say I have plastic bags. So this is my plastic bags. So this is my plastic bags. If I apply a force to these bags, so and this bag is made of polyethylene, which is a change of molecule made out of change molecule. So this force will be eventually be not force. So these plastic bags will eventually be extended until a longer length. So this is longer length, which is longer from its original length. So this is what we call plastic deformation. Okay, so that is the meaning for the plastic deformation. So in terms of the lattice atom, so let's say this is the lattice atom for the object. Okay, so this is the lattice atom. So what if I apply a large force here? So eventually this lattice atom will be slide over one another. Okay, so this is the lattice atom and this one is the slided lattice atom. So as you can see that this lattice atom is sliding over one another. So this is what we call deformation of lattice atom. So by saying that this atom will not return to its original shape. Okay, so this is the meaning for the deformation of solids. Okay, so let us proceed to the next part. So let's talk about stress and strain. So let us begin with stress. So what is actually the meaning of stress? So stress is actually defined as the longitudinal force per unit cross-sectional area acting on the wire. So this is the meaning for stress. So in terms of the formula, stress is actually given as the longitudinal force per unit cross-sectional area. So this formula is actually same as pressure. So it means that we apply stress to the wire or we apply the pressure to the wire by extending it. Okay, so this is the meaning for stress. So let me give an example about stress. Okay, so let me erase this one. Okay, this one as well. So let's say I have a wire. So this is my wire. So this wire has a cross-sectional area A. So if I apply a longitudinal force to this wire, so eventually what we get is actually smaller cross-sectional area. Okay, so this is A prime. So as we can see that stress is actually equals to longitudinal force divided by the cross-sectional area. Okay, if our stress is bigger, so the cross-sectional area we got is actually smaller. So we can conclude that after after apply after apply so sorry so after applying the stress, so uh, the cross-sectional area we got after applying the stress is actually less than the original cross-sectional area. So this is how stress works. Okay, so let me erase this one. Okay, oops. Okay, so this one as well. Okay, so let's talk about strain. So strain is actually describing about the length of the wire after the force is applied to the wire. Okay, strain is actually defined as the extension per unit's original length. By saying that strain is actually equals to the extension divided by the original length. So this is the meaning for strain. So if we apply the force for the wire, so this force, so we know that this wire will be longer after we have applied the force to this wire. So what we get is actually a longer wire. So this is L2, L1. So L2 basically is longer than L1. So this is how strains works. By saying that extension is actually depends on the original length. Okay, so let me erase this one. Okay, so this one as well. Okay, so let's move on to the next part. Okay, before we enter the next part, we need to know that what is actually the elastics limits. But on the next part, we also have to discuss about the elastic limits again. So let me briefly explain about what is the elastic limits. So elastic limits, as we mentioned from the earlier, by saying that um, so by saying that before the elastic limits, the object by saying that the object is still able to return to its original shape if the force is released. So this is the RELEASED. So this is the elastic limits. So briefly understanding at this part, so we will explain again on the next parts. So so let's talk about extension force graph So this is the stress strain graph. Stress strain graph. So this graph is actually two different things. Okay, for the extension force graph, let's say we have an object which is have the extension force graph. Okay, so let me label it. So let's say we have an object which have the extension force graph curve, which is like this. So this is okay. So this is A. I label this as A, and this is my B. So this is actually C, and this is D. Oops, I should draw this curve higher than D. Okay, so this is a curve here. So this is E. Okay, so what about stress strain graph? So this is an example for an object. Not object, should be materials. So this is the graph of that material. Okay, so this should be A, and this is B, and this is C, and this is D, and finally E. So this, from this C, we have the dotted line which is attached, which is attached to the upper part, slightly upper part from the origin. So this C is okay. So this is the attached to the strain axis. Okay, so this is my E. Oops, okay, let me write it clearly. So this is my E, which is the object has already extended a bit after the force has been released. Okay, so this is the origin. So this is my E over L. Okay, so let's talk about point A. So point A, we define it as the proportional limits. Proportional limits. So in this point A, we know that it actually obeys Hooke's law. Hooke's law, by saying that F is directly proportional to the extension. Okay, and we need to note that Hooke's law is only applicable if the object does not exceed the proportional limits. So this is how proportional limits works. Okay, let's proceed to point B. So what is actually point B? So point B is we mentioned just now, which is elastic limits. So elastic limits is where the maximum stress, oops, this one should be stress. Okay, so this one should be stress. Okay, so this one is the maximum stress. Maximum stress here, it means that it's the point where the maximum stress applied when the object is still able object is still able to return to its, let me scroll it down, to its original shape. So this is the point where maximum stress applied, but in the condition that the object is still able to return to its original shape. So as for point A, which is proportional limits and its obey Hooke's law, so this point is also, of course, will return to its original shape when the force is released. So this is for point A and B. So let's move on to point C. So point C is actually where the point we call yield point. Yield point. So this yield point is the point where the plastic deformation starts. So as we can see that, and I mentioned just now a bit about this point. So this point C, as we can see that, as the object reach the point C, and when we release our force, so this object will not able to return to its original shape, and insteadly there is an extension, a slightly extension from its original length. So this is what we call the yield point. So from this yield point, we also know that permanent deformation occur. Permanent deformation. So this is where the permanent deformation starts, and which the object will not return to its original states, and as the lattice atom begins to, how should I say, begins to sliding over one another. Okay, so this is point C. Okay, let me erase this one. So this one, let me erase it. Okay, so this one as well. Okay, so this should be straight. Okay, so let me, okay, let me erase for point C so that I have a larger space. Okay, so let's move on to point D. So this point D is the point where we call breaking stress. Breaking stress. So this breaking stress is the point where the maximum force applied to the material. Maximum force applied to the material. So as we extend, we apply force to this object, and the object begins to extend until the object become very long, which is have a very large, a very long length. Okay, so and at the same time, so this is the place where the object has its maximum length and also maximum deformation. not enough space here. Okay, so this is the maximum length and the maximum deformation point. So this is what we call breaking stress. Okay, after the point of breaking stress, so we can see that for E, and eventually we know is where the point means the object breaks. Okay, so this is all the points for A, B, C, D, E for an object, for, or should I say, material. So D is the breaking stress, and finally the object breaks at point E. Okay, so let me erase this one. So let me erase this one and this one as well. Okay, so let me give an example. Give the example for many types of material. So this is, and this should be stress and strain. Stress and strain. So this is the graph of stress and strain for steel. So let me use another color. So, okay, so this one should be and this one should be copper. So this one shall be glass. Oops. And finally we have rubber. So this graph is not according to the scale. Okay, so this curve should be outside. Okay, let me use. So this curve should be outside, inside the axis. Okay, so this is rubber. Okay, so from here, let me draw another. So let me draw another graph for extension force. Since this two graph is extremely important for us to represent all the materials. Okay, so this is the extension. So this is our rubber. So rubber will have the highest extension. Okay, so what's next? So this is our glass. So this glass is actually a straight line. So okay, so glass is actually a straight line, so that you are able to see it clearly. Straight line. Okay, so what's next? So we have copper. So copper, the graph we got is actually, oops, this one should be, okay, let me erase this one. Okay, so let me use a straight line here. So this is a straight line. Okay, so after straight line there's a curve here, and this is copper. So finally we have steel. So same, this is the proportional limits. Okay, so this is a proportional limits. Okay, so this one is steel. Okay, so this is all about um, this is about many type of example of the material. So we need to note that copper, for this copper and glass which we focus on, so we need to note that copper is actually ductile. So I'll explain what is the meaning of ductile and brittle. Okay, so this is two important keywords which we need to remember. So so let me so let me explain about this. So we can see that steel, we have a maximum stress for steel, and this glass is actually only have a proportional limits. Okay, so move on to this extension force. So we can see that rubber is actually have the maximum extension, and this, okay, so let me draw longer. Okay, so this rubber has the maximum extension among these four materials. Okay, so steel has steel has the maximum force which can be extended. Okay, so as for glass is only a proportional limits. As for copper, which is less than the maximum force is actually less than the steel. Okay, so this is the two graph which we need to memorize. Even for me is not able to memorize for these two graphs, so just try your best to memorize this graph. Okay, so let me erase this one. Okay, so let's talk about what is actually the ductile means. While another keyword is brittle, as we mentioned from previous part, and this one should be copper, and this one is our glass. Okay, so what is actually meant by ductile? So ductile is actually defined as the property of a material that undergo plastic deformation before breaking. So while brittle is the property of a material which breaks and does not undergo plastic deformation. Okay, so this is the definition for these two keywords. By saying that this copper is actually will undergo deformation before breaking. As for the glass, so we can see as we observe from that two graph as we mentioned just now. So this is actually the graph for the glass. So as we can see that the graph for the glass is actually a straight line which is only the proportional limits. So after the proportional limits, there is no more elastic limits elastic limits. Then so what else? Like the yield point, breaking stress, no. So this class is only have the proportional limits. Proportional limits. So after the proportional limits, and it will breaks directly without undergoing any deformation. So this is the property of glass. Okay, so let's move on to another parts. So we have done for these two. Okay, so let me erase this one and this one as well. Okay, so let's move on to polymeric materials. Polymeric materials. So polymeric materials is actually, as we mentioned just now, which is rubber, for example, or plastic. So this too is actually made out of polymeric material. So this too is actually made of, so let me, okay, made of strong molecular change, as we observe from chemistry. Strong molecular change. So its molecule is a chain molecule, so which will produce a large, which will produce large extension. Okay, so oops, this one is not plastic. Plastic is actually one of the example of. Okay, so this one should I write polyethylene? So polyethylene, the example for polyethylene is actually plastic, which is plastic bags, plastic bags, plastic bottles, plastic bottles, and so on. Okay, so this is the example for polyethylene. So this too, although is made out of polymeric material with the same property of for these two, which is rubber and polyethylene, but they still have the different graph, which is stress strain graph. So let's talk about rubber first. Stress. No, sorry, this one should be stress. STRESS, STRAIN. So this is for the rubber. So as we can see that if we apply the stress, or should I say, I apply a work done, which is load. So this is the stress for the rubber, as we observed from the graph just now. So when I release my work stress, so it will eventually returns to its original shape. So this is what we call unload. Okay, this is for the rubber. And as for polyethylene, and this one is the stress strain graph, of course. Strain. Okay, as we apply the work done to this polyethylene, so what we got is actually same as the rubber, but as we unload, it will eventually give us this. So actually the polyethylene will not able to return to its original shape until after we unload our stress. So that is the big difference between these two graphs. Okay, within these two graphs, there's an area here, and this one is the area. So this area represents, so let me write it here. So this area represents the energy loss per unit volume, the energy loss per unit volume in the form of heat. So there's a heat loss or energy loss per unit volume in the form of heat after we unload the rubber or polyethylene. Okay, so there is a heat dissipation. Okay, so we have done for polymeric materials. So let's move on to, okay, so let's move on to Young modulus. Young's modulus. So Young modulus is actually described about the stiffness of the object. Okay, so as we can see that from the stress strain graph. Okay, let's say I have a stress strain graph. Stress strain, and let me take an example of copper. So this one is copper, and we know that this is the point before the elastic limits. Not elastic limits, should be here, proportional limits. So as we can see that within this point, before this point, which is point A, before point A, stress is actually directly proportional to our strain. So stress is actually F over A, and this will be directly proportional to extension over the original length. So in terms of equation, F over A is actually equals to a constant which is called Y. So E over L. So Young modulus is actually equals to stress over strain. So this is the Young modulus. So Young modulus is actually described about the stiffness of the object. So as the object has the highest stress, it means that the object has the highest stiffness or highest Young modulus. Okay, so this is how the Young modulus works. Okay, so let's move on to the next part. Okay, so let's move on to our last part, which is strain energy. Strain energy. So let's say I have a force extension graph. Force extension. So this is my copper graph for the force extension graph. Okay, so this is the proportional limits. So as we know that this is F and this is E. So in this, from this region, we can see that we need to find this area. So it is actually 0 to E. 0 to E. We integrate this area from 0 to E. So this is actually F. So this extension is denoted as X. So change in X. And F, we know that is actually equals to Kx, which is the extension dx. So this is half Kx squared E 0. So this is finally we got is actually this one. So this is what we call strain energy. So, or you can say that from this area is actually a triangle area. So this triangle area is actually is our energy, strain energy, which is half times the force applied times the extension. So F is actually equals to Ke. So this one is another E. So finally we got Ke squared. So this two explanation is also applicable. So this strain energy is actually means that the total work done to produce the extension of E, to produce extension E. So this is the total work done to produce extension E, but in the condition, of course, the proportional limits must not be exceeded. Okay, so this is what we meant by strain energy. Okay, so as we have the force extension graph, so what about stress strain graph? So let me erase this one and this one as well. So what if the stress strain graph? So stress strain graph, okay. So this is just an example, not okay. So this is an example. So I don't know which this curve is what materials belongs to. So this is just an example. So okay, so this is the area before the proportional limits, not before proportional limits, before the elastic limits. So this is A, which is the proportional limits. So as we can see that this from this triangle, so in this triangle, the area of this triangle is actually what we call strain energy per unit volume, by saying that strain energy per unit volume is actually equals to the half times stress. Oops, this one should be strain times strain. So this one is F over A, and this one is E over L naught. So this is the final formula. So this is the strain energy per unit volume. Okay, so So we have done for strain energy per unit volume, and we have done for this all chapter. So I hope you can understand after watching this video, should understand further. Okay, if there's any question need to be asked, so please comment in this below this video. So I'll see you in the next video. So okay, bye.